All right, welcome to the second class of CS4510, automaton complexity. Yesterday we did kind of only an introduction. We did DFAs, and we noted that maybe they might be kind of weak in their power. Today we're going to talk about another kind of automaton, and we're going to increase the power of a DFA and see if that gives us anything. So first to begin, our automaton, the DFA had only a few moving parts, right? It was what? It had a set of states, it had an alphabet, it had a distinct start state, it had a transition function, and then it had a selection of the states which were denoted as the final states. So this was just the whole DFA in general, but of these parts, some are more important than others. Right, like let's say we were trying to have some kind of computer, trying to give it more power. We're trying to let it to do things. So which of these things can we really change to do anything with? Q and sigma have to remain finite because the size of the program has to remain finite. Q0 is just a start state. It doesn't really do anything. And F is just some selection of the final states, of the states themselves. So that doesn't really change anything. Really, the only part that's important is delta. Delta is like the only thing that does any moving. It's the only thing that does really the computation. The transitions themselves are the important part. So what we're going to do is try and change delta in 3 ways and see if that gives us any power. We're going to change in 3 ways. So first what we're going to do is we're going to allow it to not be well defined. If we need some transition and it's missing, we'll just call that an implicit rejection.
Just like a self loop?
So the question was, is implicit rejection like a self loop? Actually, it's a self loop would be skipping it. An implicit reject, so let's suppose we have some really complicated DFA. You know, when you write a program, right, you cannot have undefined behavior in a C program because that's bad and people get mad at you if you don't have your try, catch, whatever, right? I don't care, and since learning about nondeterminism, it's made me a worse programmer because you need to have, when you draw a DFA, all transitions being defined is analogous to making sure your program does have everything try and catch, right? So analogously, let's say we had some really complicated looking something like this, and then we wanted just some massive cases to just exit 0, just return immediately. The way we would denote that, let's say that was the final state or something. The way we denote that is we would have some purgatory state, and you just enter it, and you can't leave it, right? The problem with that is it's obvious what the state is doing, but it's really ugly. It makes everything really complicated and ugly. So what we can do is just ignore it. We just like say we don't draw it, and we can just pretend it's there. So anytime we see some transition, maybe all these other transitions were A's, and then anytime we see a B, we want to just leave, right? We want to always reject. We would have to do some kind of purgatory state like this in a DFA. In an NFA, one of the things we can do is just ignore it. So we don't have to draw it. And by not drawing it, we've saved ourselves quite a bit of usability in our own programmingness. We can just draw the part of the DFA that we care about, the A's in this example. So like if we did the language, I think it was like L1, it was like W is in sigma star. And what was it? W begins with an A. Right? If you recall, the DFA for this would have been, we had 2 purgatories. And if you went to the good one or the bad one, was dependent upon the first character. Right? So if you begin with an A, congrats, you stay there. We don't care about what else you see. If you see a B, you go to here, and we don't care about what else you see. But we use the double circle to denote that is a good one. That's the final state, and this is the bad one. This is the DFA. For the NFA, we would do this. We just see the A, and we do this. Right. So that this is an NFA, excuse me, would accept all strings that begin with an A. If we're at the start state and we see a single B, what do? We just implicitly reject. There's nothing for us to do, so we just say, okay, we're done with that one. Now, what if we like had this NFA, no self loop? So that would accept all strings that are just A, because if you saw A, B, you go A, you see a B, well, now you have to leave, paradise. You go B and you leave. You're done, right? So implicit. This is implicit rejection. Lets us draw the parts of the DFA that we care about for this. So this is one extension we're going to make of our syntax for the automaton. The second one is going to be what we're going to call is Epsilon Transitions. Now, what is an epsilon transition? So every transition costs something. It costs 1 unit of the string, the next letter of the string to use it. But we want to allow ourselves to take 0 of the string as well. So what we're going to do is we're going to say, like, let this be something, right? Let's say we have an A there. I'll draw it here. And let's say we have, like, B, right? So what strings is this going to accept? This is going to accept A, B. It's also going to accept A. And then it's going to accept ABB, ABBB, and so on. It would not accept like ABA, for example, because you would do A, B, and then A, and then you would leave, paradise. But what we do is we allow what's called an epsilon transition. An epsilon transition basically means you can take the transition for free without reading part of your input. So, and there's many games like Chutes and Ladders or whatever. You land on a square, you can slide to another square, right? You just get to, like at the airport, they have those things, the flat escalators. I don't know what they're called. You're not escalating up. You're something. Yeah. So you're right here. You can choose to take the epsilon or choose not to take the epsilon. So it's not forced either. If you're at this point, you can choose whether to take the epsilon or not take the epsilon. So suppose you didn't take the epsilon. To reach a final state, you would have to read an A off the front of the input, and you would then accept the same strings. You would still accept all these strings. But because we have an epsilon comma A, here you could choose not to take the epsilon. You could choose not to take the A. It's basically like a toll, but there's now a button where you could bypass it. You now say, I don't want to pay the toll. I'm going to just take the epsilon transition. And then I'm going to do whatever I want. So I'm here, I take the epsilon, and then I can take as many B's as I want. That means I'm also going to accept not just A, AB, ABB, ABBB, but the empty string is going to be accepted. Why? Empty string, done. It's going to accept B. It's going to say BB. It's going to accept BBB, and so on. So in some sense, the non-deterministic computation, choosing to or not to take the epsilon here, is analogous to choosing to accept a string that has or hasn't the A in front of it. It gets to choose. It basically gets to choose if that A is there, whether it wants it or not. So this we're going to extend it in 3 ways. This one appears to just be like a programming helping way. This seems very immediately powerful. It seems very superior, and hopefully we can build a computer more powerful than a DFA. We don't know yet. And our third and final thing is we're going to allow non-deterministic transitions. This is the whole point of the NFA. So what this means is you're at some state First, we said that in a DFA, every state has to exactly one outgoing transition per element of the alphabet. So if you're at some state and your alphabet's AB, there has to be something defined if you do an A, something defined if you do a B. Doesn't matter if it's useless, but it has to be written down. We now allow we now allow undefined transitions, so that's like less than one per thing. The non-deterministic computation basically allows more than one. So what happens is just you're at some state, you see an A, you go to some state, you see an A, you can go to some other state. So before we had exactly one outgoing transition per letter of the alphabet. We allowed ourselves now 0 outgoing transitions per letter of the alphabet, and also more than one outgoing transitions per letter of the alphabet. This is much more complex than it may seem at first. So we see an A, we can go to this state or we can go to this state, right? So if we're at, let's call this like Q0, let's say Q1, let's say Q2. If we're at Q0 and we see an A, what would you guys guess happens?
Well, it seems like we would want to go to the bottom state.
Sure, but how do we go to the bottom one?
What if you just went to both?
Right. So basically, it's kind of complicated. The understanding is that it's complicated when you first learn it, but it becomes easy. You want to go to the bottom. So what we say is you go to both, basically. You can go to both at the same time. But how do you know if a string accepts or not?
Whether anyone links.
Right. So our definition is if there exists, we say we accept a string, some word, if there exists a computation path. To an accept state. It doesn't really matter how many unlimited bad rejecting computations exist of a word on an NFA, as long as there exists one accepting computation path of the word on the NFA, then we say we accept. Right? So these are the three generalizations we're going to make to our transition function for the NFA. And this is, we're hoping to build a computer that has more power, at least. So we're going to spend the first half of the lecture just on this definition of the NFA, and then we'll spend the second half on comparing it to DFAs. So what is the definition of an NFA? So it's going to be basically almost a copy-paste of the definition of a DFA with some slight modifications. So an NFA is a non-deterministic finite automata. And the N here is it's got non-deterministic behavior. This is to distinguish it from a DFA, which has deterministic behavior, right? We've basically changed our transition function. By the way, you may have heard the word non-deterministic in some other setting, like some program having non-deterministic behavior. This isn't really, this is one of those things that gets like misdefined necessarily because maybe you might think that a program having non-deterministic behavior means something about randomness. That's not necessarily true. That's just, you know, like on the same input, maybe a program does two different things. You might understand deterministic and non-deterministic in that sense. That's not really true in this class, actually. There's a very big difference between non-deterministic and randomized. By non-deterministic, we mean this sort of magical superpower thing we're doing here, this kind of crazy looking. So let's go ahead and define the parts. We have what? Q, sigma, Q0, delta, and F. So what are these going to look like? Q is going to look like what? It's going to look like some set of states, finitely many of them. Sigma is going to look like, maybe it's AB, For us, it's usually A, B. It's a finite alphabet. Q0 is an element of Q, and it's just designated the designated start state. It's not too special. You just have to start somewhere, so we just say that's the start. Delta, and here's the hard part. So for a DFA, delta went from each pair of state for each state and each symbol, you had an outgoing transition to a single state. But here we want to generalize this, so we don't have that anymore. We have what? You're going to go from a single state times not a element of sigma, but an element of sigma or epsilon. So we're going to allow epsilon transitions. Sigma union, and then we have to make this a set, so the set containing the empty string. So you can either choose an element, when you take your transition, you can either choose an element of sigma, or you can choose the to have an epsilon transition. And now, instead of going, for DFA, we can only go to a single state. So the elements of Q that are themselves single states, so we go from any symbol state pair to a single state. What are we going to go to here? We're going to go from a symbol or not a symbol and a state pair to what?
Set of states.
Set of states. What is the set of states? The power set. Yes. So we go from, instead of here we go to a single state. The elements of Q are single states. But we need to go not to a single state, but a set of states. So when we write the function this way, we talk about the set of the elements this comes from. So it's going to be the set of states. So it's going to be the power set. Right? So as an example, here we have Q0, Q1, Q2. This would be, we would write delta like delta of, we're at some Q0, and we see an A. We would write this as the set, Q1, Q2.
So
Right. Yes?
it's just the power set because the power set is like all possible sets, right?
Exactly.
So then like any set would have to be a subset of the power set.
Right.
Okay.
Exactly. We just want, so the elements, when you write the function, of course, codomain, right? The elements here are what the function maps to. Here the function maps to single states. Here the function maps to sets of states. So we need to talk about set of states for that. So we talk about it this way. If you were to write out the function itself, though, it's going to go to sets, right? Okay. So we go from set symbol, state symbol, or epsilon as well, to set. Right? Okay, so this is the formal definition of an NFA. First off, how do we execute an NFA? That's really not obvious. How do we run the NFA? That's kind of crazy. So what I'm going to do is, and non-determinism is important, not just for the NFAs, but for, like, one of the great ideas of theoretical computer science. It'll become very important later on. Yes?
F is the same, right? You just didn't.
Oh, great. Yeah, I missed it. F is just some selection of the final states. Some as a final or accepting states. So, yes?
In an NFA, can there be multiple starting states, or does there have to be one?
There is only one starting state. But it turns out, just because of the way the definition is, but it turns out that's okay that there's multiple. You could, if you had something you wanted to do with multiple start states, I claim you could do it with one start state. Why?
You just make a new start state and then add transitions to all the prior ones.
Exactly. You want to do it for free, though. So it's going to be, let's say these were your the start states you wanted.
Right.
So now you could have had multiple start states. If you start here, you now can start your computation from here or here. You can choose where to start, and you consider all computation paths on all of them that accept. So let me give you some analogies about nondeterminism because it's really, it makes people really uncomfortable the first time they see it. So first off, nondeterminism isn't real, okay? Like, we're all deterministic. We come to we have to make a choice. We make a choice. We don't get to choose both things. Usually, you have to. A program cannot be into a superposition of states at once, right? So here, you go from you're in both of these states at once. The DFA is the more physical model because you can go state to state to state. It's like you're walking around on a path, but you can't take two paths at any split in life usually. So nondeterminism, let's ignore the let's ignore the part where it's not real and just consider it as a hypothetical model, right? So it shouldn't be totally uncomfortable to us that it may not be buildable or so on. There are three main analogies to understand nondeterminism. First is with BFS. So like if you're running an NFA, you come to a fork in the road, what do? Like again, by a fork in the road, I mean like you have some symbol off your input you want to read. You have a choice of paths to make. You can choose to go up or down, you know, red pill, blue pill. You get to choose one to do. So you come to the fork in the road. What you can actually do is just BFS on it. So although the non-deterministic finite automaton might not be like buildable in the way it's defined, certainly you could write a program to simulate a NFA. Like you could very reasonably do that. And you might implement coming to a fork in the road using BFS, right? You BFS from here to here, and you just see if there's any accept state reachable from there, right? So you just search this tree. You search the NFA on your input word. For an accept state. So the problem with this is that the NFA runs in not even linear time, but straight up real time. It takes exactly the number of steps as is the size of the input necessarily. So the BFS though doesn't do that. BFS takes, you know, it costs something. Somehow you're doing maybe some really long, annoying search in the size of the graph and not the size of the word. So that's why this isn't really, buildable. Another way to think of it is the lucky coin analogy. So basically, you come to the fork in the road. You're walking on a path. You somehow have this godly device in your hand. You flip the coin, and it guesses for you. So it's like lucky guesses. Somehow you're able to guess, but you have, eaten a potion or something, and you can guess with probability 1 which is the correct path. So you always guess correctly which path will lead you to the accept state. So in that sense, it's kind of magic, but then this allows it to run in like real time, right? You only take the number of steps you want. You come to the epsilon transition, you take the epsilon transition, right? The final analogy is like, I don't know what to call it, many worlds or alternate timelines. So every science fiction whatever has different rules about how the time travel works in those things. But have you guys seen that episode of Community where he has Abed has the dice? It's got 6 sides, and basically they're like playing a board game or something annoying, and he rolls the dice, and the episode plays out with like 7 different scenarios based on what side the die rolls, right? So the die, he's like, don't roll the dice, you're going to create 6 alternate timelines. And then he rolls the dice, and the episode is basically the same thing happening 6 times as if the die landed on each of those instances, right? And in all of them, they end in like chaos and things catch on fire and people die. And then I guess the seventh time when he like catches the die, he doesn't let it roll, and he takes charge of his own destiny, or something like that. Have you guys seen this episode of Community? Maybe it sounds vaguely familiar. Okay, well, Community is not really the show, I guess, if you're looking for science fiction or alternate timelines or so on. But like basically, like you come to a fork in the road, and you now create a rift in time, and now there are now two separate, distinct timelines. One where you took the first path, and one where you took the second path. And both of those timelines continue. And somehow, you're no longer in a linear time kind of thing, like a single path of your time space, whatever. Your time space now looks like a tree. So your computation would look like a tree. And if one of those timelines accepts, then then you win. The other timelines maybe you die in, so that's okay. As long as one timeline continues, then you found the accepting path and you keep going, right? Something like this. Another way to think of it, like without all the space stuff, is like if you had some sort of multi-process system, you come to a fork in the road, you call fork or exec, right? I don't remember which one does what. And you say you restart the simulation, but with you starting here and with you starting here. So if there was two non-deterministic choices, you create two processes, two child processes that, as if they each went to each of those states. And those processes can create their own child processes and so on. And as long as one process finds an accept state, then you can close all the other child processes and everything collapses back down, and congrats, you found the accept state. Again, the multi-process kind of idea is a little complicated because it also doesn't run in exactly the number of steps that the NFA requires. Initialization, and then things are running in parallel, or are they sequential on a machine, and so on. Yes?
It's like similar to recursion, kind of.
Recursion.
You just like go down all the paths that it can.
Yeah, I guess like on the master theorem kind of thing, maybe.
Yeah, like on a tree. So like some like DFS type thing where you can
Right. So the computation path of an NFA is itself a tree. Right. So like if you're talking about a DFA, what is the computation path? If you have a specific word,
just a path.
like the sequence, there is only one sequence of states that you could go from. Right?
Right.
In a DFA, there exists exactly one computation path. But in an NFA, there exists multiple computation paths. So it could look like this. So these are not DFAs and NFAs themselves. These are just sort of analogies about what a computation path might look like. You go NFA, let's say you come to a fork in the road, you do something else. Let's say you didn't come into the fork in the road here. And then let's say you did come to the fork in the road again, something like this. And maybe let's say these all reject or something. But then like one accepts. So then we say the whole computation path of the NFA accepts. Yes?
Sorry, came to class a little late, so this might have been discussed earlier, but can multiple things be accepted in an NFA, or does there have to be only one thing accepted?
So you certainly could go to multiple accept states. That's allowed. As long as there exists one. If there exists two, that does mean there exists one. Right? So
right.
Yeah, so more than one is great. But at least one. There can't be none, basically.
Right.
If all paths reject, then the string rejects. If at least one path accepts, then the string accepts.
So is like the lucky coin like a specific example of the alternate timelines where there's only one?
Think of these three analogies as very differently. Like the lucky
Right.
coin is like you don't have any time travel, but you're always somehow in the path that was going to accept anyway, if there exists an accepting path, right?
What if there's multiple?
It will tell you one of them.
Oh, I see.
Yeah. You listen to the coin, and it'll take you to an accepting path.
Right.
Somehow. Yes. So you're in that sense you're like on the NFA itself, taking the paths that it makes you. So this is a very limited kind of form of non-determinism. Actually, it turns out you may have heard of like P and NP. NP does not stand for not polynomial. It stands for nondeterministic polynomial time. And this is the same nondeterministic that we have here. You may have had some definition about nondeterminism, not NP, in 3510 about how it's like deterministically poly-time verifiable. It turns out that's more of a coincidence, and the actual definition involves this kind of crazy computational idea, right? So at first, at least it seems that nondeterminism is like strictly more powerful than a DFA. That may seem to be the case because there's kinds of crazy things you can do with an NFA. Let's actually just, I realize we've been doing snippets of NFA, but we haven't really done like one example. So let's just do one example of an NFA. So let's do the language W is a word, and W begins with, no, not begins with. Do something slightly harder. We'll do ends with AA. So here, W is a word, it's going to end with AA. So we gave a DFA real easily for beginning with letters. We're going to give an NFA now for ending with letters. And we're going to actually create a very easy NFA, much easier than creating the DFA, by using all the magic power we have. So we're going to have some start state. We're going to guess the prefix of the string, and then accept if we see two A's. Right. So how does this work? Here, why is this, first off, why is this non-deterministic? Yes.
There's two A transitions in the start state.
Right. You go from Q0. When you see an A, you can either choose to stay in Q0 or you can choose to go to Q1. All right, we'll call this Q1, Q2. Right. You can choose which one to go to. So the self loop here is kind of important. It's kind of like the fork. How does the computation on this work? So let's say you have a string of a lot of A's. Okay, let's say you have like 10 A's. Something like this. That's 6 A's. For each A you see, and you're at Q0, you can choose to stay at Q0 or move on to Q1, right? So for each A, you're allowed to make that choice. So on a string like this, there's going to be many, many computation paths, right? Most of them are going to be, the NFA is either going to guess the string way too early or it's going to guess the string way too late. So here, it's going to, as long as there exists a computation path, the machine will accept, yes?
Why is there no self loop at the very end?
We don't care. What's cool about an NFA, I get to be lazy. I don't have to have a self loop.
Oh, it ends with an AA. Oh
Yeah, ends with an AA.
I thought it was just AA was a substring.
That would require a self loop for an NFA. Yeah, certainly. So this, we just get to guess that we're two strings from the end of this object, and we get to go there. So like if we were at this A and we guessed too early, we would go A, and then we would have more symbols. So we would hit this state, but then we would be forced to implicitly reject. If we guess like here, we would say AA, we would be forced, we would have more letters left in our word, we would be forced to implicitly reject, right? If we guess too late, let's say we guess the last A, we go to here, well, it's not an accepting state, so we would be forced to reject. But it's okay, there's so many computation paths of this word on this NFA that do reject, doesn't matter. As long as there exists one, where we can choose the NFA will choose to guess exactly when the moment is right. It'll choose right there, and then it's going to accept that computation. So there's going to be all these many, I don't want to do the math on counting how many computation paths reject, but it's fine. One of them accepts. So this machine, this NFA will accept this word. Is this believable? You guys have any questions on this one? Seems a little intuitive. Now, let's do the DFA for this one just to show how different and complicated it is. Q0, Q1, Q2. So I do want to have an AA, and I want to reach the accept state when I see an AA. But I have to now do all this error handling. I don't get to be nice and just guess where the end of the string is. I have to actually pay attention and deal with it. So how would I do that? Basically, if I see a B at the beginning, I should get to ignore it. Okay? But if I see an A, I have to be prepared if I'm going to see AA and I'm at the end. So let's say I see an A, awesome. But then I see a B. Well, the string has to end with AA, so if I see a B, I need at least 2 more letters anyway. So I'm going to have to reset myself. Now, if I'm anytime I see a B, it basically means I have to reset. So let's say I saw AAB, right? I have to reset. So what if I saw AAA? Well, AAA has AA as the end anyway, right? So great, I saw AA, I should just get to stay here. Let's see, do we have all transitions? 2 outgoing, 2 outgoing, 2 outgoing. I think that's all of them. So this DFA, so this is the NFA. And this is the DFA. So this is maybe not the best example because the only difference here between the NFA and the DFA appears to be the error handling, right? If this was like a program, the only difference between this is that this is the part of the this is the part that we care about, and this is the part that has all the error handling in it, right? We have to be prepared at any moment if we're not ready to end. We don't just get to not care about those computation paths. We have to handle all of the outgoing transitions, right? So this looks like this one, but with the error handling built in, right? So if I were to actually try and write a program or something, I would care a lot more about writing the NFA than I would about writing the DFA. Because the DFA has got all these, personally, I'm a bad programmer. I don't like doing all these try-catch and stuff, writing good code. I prefer about the part that matters to me, So this is really one example of the power of an NFA versus a DFA, right? As another example of the power, so consider the following 2 languages. So let's say we had, I don't know, L3 is going to be, W is in sigma star, and W ends with B. Instead of AB, I'll just say with B. And let's say we had L4. W is in sigma star, and the number of B's is even. So if I wanted to make an NFA for the first language, I could do something similar to ending with A. If we can end with AA, we certainly could make something to end with B. So we're just going to do exactly that. We're just going to guess the beginning of the string. We're going to guess the beginning of the string, and then we're going to just transition from the last one. Right? So this one will accept this NFA will accept all strings that end with just a B. Now what if we did for L4, we want to do B is even. So we want to do our little kind of clock thing. Now we have to have the A's here, right? If we don't have the A's, it's not an ignore the A's, it's reject on the A. So we want to ignore the A's and not reject on them. So we have to have transitions here for the A's. That's going to give us something like this and this. And what is the accept state? This is the accept state, right? So last time we talked about how to do, like just for DFAs, how we could use the Cartesian product to construct the intersection. And also, we talked about how you could change the set of accepting states to get the union. So the Cartesian product is kind of complicated because you need, if you have two DFAs of size n and m, you now, to take the Cartesian product of the DFAs, you get a new DFA of size nm. So you take the product. You need one for each pair. Here, we need to, there's actually a much easier way to do this. So how could we make, we have two NFAs. How could we make one NFA for the union?
For the union, right? Not for the intersection?
Not the intersection, the union.
You just make that end state.
So one more time?
Actually, never mind.
Okay, so the answer is we're going to use nondeterminism to get, if we want to construct the not the union, not the intersection, the union of L3 and L4, all we have to do is nondeterministically guess which one we're going to run it on. So new start state. So if there existed an accepting, if the word happened to end with a B, it doesn't matter here what happens. There's going to be many rejecting ones. Who cares? But there's going to be one accepting computation path on the first part. So if a word ends with a B, it was accepted by this NFA. So then there exists an accepting computation path on now this NFA. So it's now accepted by this NFA. So anything in L3 is going to be accepted by this NFA. Similarly, anything in L4, if something was in L4, then it was accepted by the bottom. Right? There existed an accepting computation path on this bottom NFA, and that means there exists now an accepting computation path on this now bigger NFA. Doesn't matter what happens here, how many rejecting computation paths exist at the top, because there exists one accepting computation path on the bottom. We say this NFA accepts. Right? It may be the case that there are accepting computation paths at the top. There may be a word that ends with a B and has an even number of B's. That's fine. That's not like illegal, because as long as there exists one accepting computation path, it's going to work out. Right? So this is a way you can quickly do the union of two NFAs to get the union of the languages. Yes?
So every DFA is an NFA, right? It's just a tighter.
Ah, yes. So let's talk about that. Why is every DFA is an NFA? Why?
It's just a tighter set of restrictions on the NFA delta set.
Yeah, exactly. So every DFA is an NFA. The DFA is just a restricted form of the NFA, or you can think of the NFA like a direct generalization of the NFA, a direct generalization of the DFA. So the definition of a DFA, if you take any NFA, if you take any DFA, the definition of a DFA is going to satisfy the exact definition of the NFA. But there may be NFAs which aren't DFAs, right? Any NFA with a nondeterministic transition, any NFA with epsilon transitions, these aren't DFAs. So every NFA, there exist NFAs which aren't DFAs, but every DFA must be an NFA. So the NFA is a direct generalization of the NFA, right? I said it backwards again. The NFA is a direct generalization of the DFA, right? So let me give you one kind of one more final explanation to nondeterminism, and then we'll go on our little break. There's this poem by Robert Frost that I love a lot. Let's see if So The Road Not Taken by Robert Frost is this poem, and it says, the road not taken. So two roads diverged in a yellow wood, and sorry I could not travel both. And be one traveler, long I stood, and looked down one as far as I could to where it bent in the undergrowth. Then took the other just as fair, and having perhaps the better claim, because it was grassy and wanted wear. Though as for that the passing there had worn them really about the same. And both that morning equally lay, in leaves no step had trodden black. Oh, I kept the first for another day. Yet knowing how way leads on to way, I doubted if I should ever come back. I shall be telling this with a sigh. Somewhere ages and ages hence, two roads diverge in a wood, and I took the one less traveled by, and that has made all the difference. So in this poem, like, you have Robert Frost, he's just a guy, right? So it's like, I should zoom back out. Right, so like the moral is like Robert Frost is this guy. He comes to a road, and the two paths look very different. Like maybe one is nice, it has nice grass or whatever, and like the other one, I don't know, maybe it's scary or something. And then the guy comes to the road, you know, he's trying to get food or something, and he doesn't know which path to take. He's like, he can go left or he can go right. But in either way, Robert Frost, this guy is a deterministic actor. And because he's deterministic, he's forced to choose. Which way does he go, right? He has to, and at the end, he ends up choosing one of the paths, and he talks about his little choice about choosing the path. But it's clear from the poem that he is deterministic. He can't travel both, and he's only one traveler. So he's forced, essentially, since the fact he's deterministic, he's forced to make a choice. If Robert Frost in the poem was non-deterministic, then he could just come to the fork in the road and then just take it. So he wouldn't have to choose. There's no thinking involved. He just goes on the path. He takes both paths, and he ends out at wherever he was supposed to be, wherever he was meant to be. Okay? We're a little early, but I think we'll take our break now.